In the world of quantum physics, one of the most puzzling and fundamental concepts is wave-particle duality. This idea suggests that particles like light and electrons do not exist solely as particles or waves, but can exhibit characteristics of both, depending on how they are observed. This paradoxical nature challenges our classical understanding of the physical world, where entities are typically classified strictly as either waves or particles. Wave-particle duality is not just a curious anomaly, it's a cornerstone of quantum mechanics that helps explain phenomena at the smallest scales of nature. The journey into wave-particle duality began in the early 20th century, during a time when physicists were grappling with the nature of light. Prior to this, light was considered to behave purely as a wave, with phenomena like interference and diffraction being strong evidence of its wave-like nature. However, in 1905, Albert Einstein published a paper that revolutionized our understanding of light. Building on Max Planck's work on black-body radiation, Einstein proposed that light could also be thought of as discrete packets of energy called photons. This explanation successfully accounted for the photoelectric effect, where light striking a metal surface ejects electrons, an observation that could not be explained if light were only a continuous wave. Einstein's idea of light as both a wave and a particle was a crucial step in the development of quantum theory. It led to the understanding that the concept of wave-particle duality applied not just to light, but to all particles at the quantum level, including electrons, protons, and even atoms. In this strange quantum realm, entities don't fit neatly into the classical categories of waves or particles. Instead, they exhibit properties of both depending on how they're measured. The double-slit experiment is one of the most famous and striking demonstrations of wave-particle duality. First performed by Thomas Young in 1801 with light, this experiment revealed the wave-like behavior of light. When light passed through two narrow slits, it produced an interference pattern on a screen, as waves do when they overlap. This pattern suggested that light was behaving like a wave, with the crests and troughs of the waves reinforcing or canceling each other out. However, the story took a strange turn when the same experiment was conducted with individual particles of light, photons, or even electrons. If particles were fired one at a time through the slits, one might expect them to produce two simple spots on the screen, corresponding to the two slits. But the result was a pattern identical to what was seen with waves, an interference pattern, indicating that each particle was somehow interfering with itself as though it were a wave. What's even more perplexing is that when detectors were placed at the slits to observe which slit the particles passed through, the interference pattern disappeared, and the particles behaved as expected in classical physics, either through one slit or the other, not both. This suggested that the act of measurement or observation was causing the particle to choose a behavior. Before observation, the particle seemed to exist in a state where it was both a wave and a particle at the same time, a state known as superposition. This bizarre outcome led to the conclusion that the wave-particle duality is not a simple choice between two behaviors, but a complex interaction influenced by observation. When unobserved, particles exhibit wave-like properties, but once measured, they collapse into a particle-like state. The quantum description of objects such as electrons is very different from how we think about everyday objects. Classical particles like marbles or baseballs have a definite position and momentum, and they obey Newton's laws of motion. But quantum particles, including electrons, don't have definite positions or velocities until they are measured. Instead, they are described by a wave function, a mathematical function that encodes all the possible positions, velocities, and other properties the particle might have. When a quantum particle is not being observed, it exists in a superposition of all of these possibilities, behaving like a wave that can spread out across space. This wave function describes a probability distribution where the particle is likely to be found when measured. The wave-like behavior shows up in phenomena such as interference and diffraction, where particles act like waves that interact with one another, leading to the observed patterns. Yet, when an observation is made, this wave function collapses and the particle is found in one specific state, such as a particular location. This collapse of the wave function and the shift from a wave-like to a particle-like state is a key feature of quantum mechanics and is part of what makes wave-particle duality so strange and counterintuitive. Wave-particle duality has profound implications for how we understand the universe. At the heart of quantum mechanics, it challenges the very notions of reality, measurement, and causality that we take for granted in the macroscopic world. It forces us to reconsider the idea that objects can be classified definitively as either waves or particles. In the quantum world, the behavior of a system is fundamentally dependent on how it is observed. This brings us to deeper questions about the nature of reality itself. One interpretation of wave-particle duality is the Copenhagen interpretation, which asserts that the wave function represents our knowledge of the system and the act of measurement determines the system's state. According to this view, before measurement, a quantum object exists in a superposition of all possible states, and it is only upon observation that the wave function collapses to a definite outcome. This has led to debates about whether the act of measurement is a passive observation or an active creation of reality. Another interpretation, the many worlds interpretation, suggests that all possible outcomes of quantum events exist in parallel realities, with each observation splitting the universe into a new branch. In this view, wave-particle duality is just an expression of the different possible realities that emerge from quantum events. While wave-particle duality is widely accepted in quantum mechanics, it remains one of the most baffling and philosophically challenging aspects of modern physics. The fundamental nature of particles, waves, and reality itself is still a topic of debate, and wave-particle duality serves as a reminder that our classical understanding of the world is inadequate when it comes to describing the quantum realm. The double-slit experiment is one of the most famous and perplexing experiments in the history of science, and it reveals some of the strangest and most fundamental aspects of quantum mechanics. The experiment demonstrates the wave-particle duality of matter and light, showing that particles, such as photons or electrons, can exhibit both wave-like and particle-like behaviors, depending on how they are observed. This experiment is often cited as one of the most puzzling and thought-provoking results in all of science, because it challenges our most basic intuitions about the nature of reality. The double-slit experiment dates back to 1801, when Thomas Young performed it with light in order to demonstrate the wave-like nature of light. Young's original experiment passed light through two narrow slits, and the light waves emanating from these slits produced an interference pattern on a screen behind the slits. The pattern consisted of alternating light and dark bands known as interference fringes, which are characteristic of wave phenomena. This was a strong piece of evidence that light, which had previously been considered to be a stream of particles, as suggested by Isaac Newton, was actually a wave. At the time, the concept of light as a wave was groundbreaking. It helped to explain phenomena such as diffraction and interference, which were difficult to account for if light were only considered to be particles. However, light's wave-like nature was not the only discovery that came from the double-slit experiment. When the experiment was repeated with individual particles such as photons or electrons, something completely unexpected occurred. If light or electrons are treated as discrete particles, one might expect that when fired through the slits, each particle would either go through one slit or the other, and the result would simply be two spots on the screen, one behind each slit. But what was actually observed was far more surprising. Even when particles were fired one at a time, they did not create two distinct spots, as expected. Instead, they created an interference pattern, just as waves of light do. This was a major mystery. How could a single particle traveling alone create an interference pattern? This suggested that the particle was somehow behaving like a wave and was passing through both slits simultaneously, interfering with itself on the other side. This behavior is a central part of wave-particle duality, the idea that quantum entities, such as photons and electrons, exhibit both wave-like and particle-like properties depending on how they are observed. This phenomenon has been at the heart of quantum mechanics since its inception. It implies that particles, when not being measured, exist in a state that is neither purely a wave nor a particle, but rather a superposition of both. The truly baffling part of the double-slit experiment comes when a measurement is made. If detectors are placed at the slits to determine which slit the particle passes through, the interference pattern disappears. Instead of behaving like a wave that passes through both slits, the particle behaves as a classical particle and travels through one slit or the other. When we measure the particle's path, it seems to choose one slit over the other, and the interference pattern vanishes. This observation of the particle fundamentally changes its behavior. The idea that the simple act of measurement can change the outcome of an experiment is a profound and strange aspect of quantum mechanics. It suggests that before the particle is observed, it exists in a superposition of all possible states, behaving like a wave that can go through both slits. But once an observation is made, the wave function collapses, and the particle behaves as a definite particle, passing through one slit or the other. This phenomenon challenges our classical understanding of reality, where objects are assumed to have definite properties regardless of whether or not they are observed. This has led to some deep philosophical questions about the nature of reality. If particles exist in a superposition of states, does that mean reality itself is somehow undefined until it is observed? Does the observer play a crucial role in determining the outcome of quantum events? These questions have led to a variety of interpretations of quantum mechanics, each attempting to answer the question of what happens when the wave function collapses. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the early 20th century, suggests that the wave function represents our knowledge of the system, and that it is only when we make a measurement that the wave function collapses to a definite state. According to this view, the act of measurement plays a central role in shaping the outcome of quantum experiments. It posits that the wave-like behavior of particles exists as a potentiality until it is measured, at which point the system chooses a particular outcome. On the other hand, the many worlds interpretation proposed by Hugh Everett in 1957 suggests that all possible outcomes of a quantum event occur in parallel, with each outcome resulting in the creation of a new branch of the universe. According to this view, the wave function never collapses. Instead, every possible outcome of an experiment exists in a separate, parallel reality. For example, if a particle passes through two slits, one universe will contain the particle going through the left slit, while another universe will contain the particle going through the right slit. Both outcomes exist simultaneously in different branches of reality. Both interpretations are controversial and have their own strengths and weaknesses, and the double-slit experiment is central to the ongoing debate about the nature of quantum reality. The very fact that the experiment seems to show that particles can behave like waves or particles depending on how they are observed raises fundamental questions about the role of the observer in quantum mechanics. Is the act of measurement an essential part of quantum events, or does reality simply split into multiple branches, with each possibility realized in a different universe? The double-slit experiment has had a lasting impact not only on our understanding of quantum mechanics, but also on the development of quantum technologies. For example, quantum computing exploits the principle of superposition, where quantum bits, qubits, can exist in a superposition of states, allowing quantum computers to process much more information simultaneously than classical computers. Similarly, quantum cryptography relies on the principles of quantum mechanics to create secure communication systems that are fundamentally unbreakable, because any attempt to measure a quantum system inevitably alters it. Despite its success in the development of quantum technologies, the double-slit experiment remains a source of mystery. It is not just a scientific experiment. It is a window into the deepest questions of philosophy and metaphysics. It raises questions about the nature of observation, reality, and the relationship between the observer and the observed. Is the universe a deterministic system that operates according to laws of cause and effect? Or is it a probabilistic system that can only be understood in terms of probabilities and uncertainties? Quantum superposition is one of the most fundamental and intriguing principles in quantum mechanics. It refers to the idea that a quantum system can exist in multiple states at the same time, rather than being limited to just one. This principle challenges our classical understanding of how objects behave, where an object typically exists in a single, well-defined state. In the quantum world, however, particles and systems can be in a combination or superposition of all possible states until they are observed. The phenomenon of quantum superposition has profound implications for our understanding of the nature of reality and the limits of our ability to predict and measure physical systems. At its core, quantum superposition means that particles, such as electrons or photons, do not have definite properties until they are measured. Instead, they exist in a range of possible states that are described by a mathematical function called the wave function. The wave function contains all the possible configurations a quantum system could take, and the system's actual state is determined only when a measurement is made. This idea is drastically different from classical mechanics, where objects always have a definite position velocity, or other measurable properties at all times. One of the most famous thought experiments that illustrates quantum superposition is Schrödinger's cat. In this thought experiment, Schrödinger imagines a cat inside a sealed box, along with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of poison, killing the cat. If the atom does not decay, the cat remains alive. In classical terms, the cat is either alive or dead depending on whether the atom decays or not. However, in quantum mechanics, the radioactive atom is in a superposition of both decayed and undecayed states until it is measured. Therefore, according to quantum mechanics, the cat would also be in a superposition of being both alive and dead until the box is opened and the system is observed. The idea that a macroscopic object like a cat could be in two contradictory states at the same time seems absurd in the classical world, but in the quantum world, superposition is a real and experimentally verified phenomenon. This is because quantum systems are typically studied on much smaller scales, where particles like electrons can exist in superposition. For example, in the famous double-slit experiment, when electrons or photons are not measured, they pass through both slits simultaneously, as if they were in a superposition of both possible paths. However, when they are measured, they collapse into a single state, passing through one slit or the other. Quantum superposition is not limited to particles like electrons and photons, but can also apply to larger, more complex systems. However, as systems increase in size, they tend to interact more strongly with their environment, causing them to decohere and lose their superposition states. This phenomenon is known as quantum decoherence. The superposition principle is therefore most apparent in isolated quantum systems, where there is minimal interaction with the external environment. The mathematical framework of quantum mechanics provides a way to calculate the probabilities of different outcomes of a quantum system. The wave function that describes the system is a superposition of all possible states, with each state being associated with a certain probability. When a measurement is made, the wave function collapses to a single state, and the system is found in one of its possible configurations. However, the system was not in a definite state until the measurement occurred. Instead, it was in a superposition of all possible states. This collapse of the wave function when a measurement is made is one of the most mysterious aspects of quantum mechanics. The act of measurement appears to cause the system to choose a specific state from the superposition of possibilities. This process is often referred to as wave function collapse. The idea that the mere act of measurement can affect the outcome of an experiment has led to a number of different interpretations of quantum mechanics, each trying to explain what happens during the collapse of the wave function. One of the most well-known interpretations is the Copenhagen interpretation, which was developed by Niels Bohr and Werner Heisenberg in the early 20th century. According to the Copenhagen interpretation, the wave function represents the probabilities of different outcomes, and it is only when a measurement is made that the system chooses a definite state. The observer plays a crucial role in determining the outcome of the quantum process, and until the system is observed, it exists in a superposition of all possible states. Another interpretation is the many worlds interpretation, proposed by Hugh Everett in the 1950s. In this view, the wave function does not collapse. Instead, all possible outcomes of a quantum event occur in parallel universes, with each outcome being realized in a different branch of reality. According to this interpretation, the universe splits into multiple versions of itself, each corresponding to a different state of the quantum system. In the context of Schrödinger's cat, for instance, one branch of the universe would contain the cat alive, while another branch would contain the cat dead. Both outcomes occur simultaneously, but in separate, non-interacting branches of reality. Despite the differences between these interpretations, they all agree that quantum superposition is a fundamental aspect of the quantum world. Superposition allows quantum systems to exist in multiple states at once, and the measurement process causes the system to collapse into one of these states. The probabilistic nature of quantum mechanics, along with the idea of superposition, means that we can never predict with certainty the exact outcome of a quantum event. Instead, we can only calculate the probabilities of different outcomes, and the actual result is only determined once the system is observed. Quantum superposition has important implications beyond just our understanding of the behavior of particles. It also plays a crucial role in emerging technologies such as quantum computing. Quantum computers rely on the principle of superposition to process information in ways that classical computers cannot. While a classical bit can exist in one of two states, 0 or 1, a quantum bit, or qubit, can exist in a superposition of both 0 and 1 at the same time. This allows quantum computers to perform many calculations simultaneously, potentially solving problems that would be infeasible for classical computers to handle. Quantum superposition is also central to the field of quantum cryptography, which uses the principles of quantum mechanics to create secure communication systems. In quantum key distribution, QKD, for example, the security of the communication relies on the fact that any attempt to observe the quantum system will disturb it, revealing the presence of an eavesdropper. The superposition of states in the quantum system makes it possible to detect unauthorized attempts to intercept or measure the communication, providing a level of security that is impossible to achieve with classical methods. Schrödinger's cat is one of the most famous thought experiments in the history of quantum mechanics. Proposed by the Austrian physicist Erwin Schrödinger in 1935, it was designed to illustrate the paradoxes and counterintuitive nature of quantum mechanics, especially the concept of superposition and the role of observation in determining a system's state. The thought experiment has since become a symbol of the strange and baffling phenomena that occur at the quantum level, highlighting the tension between quantum theory and classical intuition. The setup of Schrödinger's cat experiment is deceptively simple. Imagine a sealed box containing a cat, a radioactive atom, a Geiger counter, and a vial of poison. The Geiger counter is set to detect the decay of the radioactive atom. If the atom decays, the counter triggers the release of poison, killing the cat. If the atom does not decay, the cat remains alive. The critical aspect of the experiment lies in the fact that the decay of the radioactive atom is a quantum event, meaning it is governed by the principles of quantum mechanics, where the atom can exist in a superposition of both decayed and undecayed states simultaneously until it is observed or measured. In quantum mechanics, particles like atoms do not have definite states until they are observed. Instead, they exist in a superposition of all possible states, each associated with a certain probability. In the case of the radioactive atom, until it is measured, it can be in a superposition of both decayed and undecayed states. According to the principles of quantum mechanics, the cat inside the box should also be in a superposition of both alive and dead states. As the cat's fate is linked to the state of the atom, it's not until the box is opened and the system is observed that the cat is either found to be alive or dead. Until then, it is simultaneously alive and dead, existing in a superposition of both possibilities. This thought experiment was Schrödinger's way of illustrating the paradoxes that arise when quantum mechanics is applied to macroscopic systems. In classical mechanics, we expect objects to have well-defined states at all times. A cat is either alive or dead, and it is inconceivable that it could be in both states at once. However, in the quantum world, systems can exist in superposition, where they are in multiple states simultaneously. Schrödinger's cat challenges this intuition by applying the principles of quantum mechanics to a situation involving a living organism, an example that we can more easily relate to in everyday life. The key to understanding Schrödinger's cat paradox lies in the nature of quantum measurement. In quantum mechanics, particles like atoms are described by a mathematical object called a wave function, which encodes all the possible states of the system. When the system is not being measured, the wave function evolves over time according to the Schrödinger equation, describing a superposition of all possible states. It's only when a measurement or observation is made that the wave function collapses, and the system assumes a definite state. In the case of Schrödinger's cat, the system is composed of both the cat and the radioactive atom, and the wave function describing the system evolves to include all possible combinations of states, the atom being decayed or undecayed, and the cat being alive or dead. According to the Copenhagen interpretation of quantum mechanics, the act of measurement, in this case opening the box and observing the cat, causes the wave function to collapse, and the cat will be found in one of the two possible states, either alive or dead. Before the box is opened, however, the cat exists in a superposition of both states, in an unmeasurable and paradoxical state of being both alive and dead simultaneously. Schrödinger's cat is often interpreted as highlighting the problems and ambiguities in the way quantum mechanics relates to the classical world. While quantum mechanics accurately describes the behavior of microscopic particles, it produces results that seem incompatible with our everyday experiences. At macroscopic scales, objects do not appear to be in superpositions of states. They are either one thing or another. This discrepancy between the quantum and classical worlds raises important questions about the nature of measurement, observation, and reality. The paradox has also prompted numerous interpretations of quantum mechanics, each attempting to address the issue in a different way. The Copenhagen interpretation, the most widely known interpretation of quantum mechanics, asserts that the wave function represents all the possible outcomes of a quantum system. The act of measurement causes the wave function to collapse, resulting in a definite state. According to this interpretation, until the box is opened and the cat is observed, the cat is in a superposition of being both alive and dead. The many worlds interpretation developed by Hugh Everett in the 1950s takes a different approach. Rather than suggesting that the wave function collapses upon measurement, it proposes that all possible outcomes of a quantum event actually occur, but in separate, non-interacting branches of the universe. In the context of Schrödinger's cat, this means that when the box is opened, the universe splits into two branches, one where the cat is alive and another where the cat is dead. Both outcomes occur, but in different parallel worlds. The many worlds interpretation eliminates the need for wave function collapse, suggesting that the universe is constantly splitting into new branches with every quantum event. Another interpretation is the de Broglie-Bohm theory, which proposes that particles always have definite positions, but that their behavior is guided by a pilot wave. In this view, the cat is not in a superposition of alive and dead states, but the quantum wave function guides the evolution of the system in a way that accounts for both possibilities. The cat's fate is determined by the underlying hidden variables that govern the system's behavior, even though our classical intuitions might not allow us to observe these variables directly. Despite the different interpretations, the central issue raised by Schrödinger's cat remains the same. How do quantum systems, which can exist in superposition, relate to the macroscopic world, where objects seem to have well-defined states? The thought experiment emphasizes the strange and counterintuitive nature of quantum mechanics, particularly when extended to larger systems. It also underscores the importance of observation and measurement in determining the state of a quantum system. Until a measurement is made, quantum systems are not in one definite state, but in a superposition of all possible states. And only through observation does the system collapse into a single outcome. Schrödinger's cat has also had important implications outside of quantum mechanics, influencing fields like philosophy, information theory, and even the development of quantum computing. The paradox has become a symbol of the puzzling nature of quantum mechanics, providing a way to discuss the deeper philosophical questions about the nature of reality, the role of observers, and the limits of human knowledge. In the context of quantum computing, Schrödinger's cat provides a vivid illustration of how quantum systems can process information in fundamentally different ways compared to classical systems. Just as the cat can exist in a superposition of alive and dead states, quantum bits or qubits can exist in superpositions of both 0 and 1, allowing quantum computers to perform calculations that would be impossible for classical computers. The concept of superposition, illustrated by Schrödinger's cat, is at the heart of quantum computing's potential to revolutionize technology. Heisenberg's uncertainty principle is one of the foundational concepts in quantum mechanics, introduced by the German physicist Werner Heisenberg in 1927. It fundamentally challenges our classical notions of measurement and observation, asserting that there are inherent limits to the precision with which certain pairs of physical properties, like position and momentum, can be simultaneously known. This principle is a direct consequence of the wave-like nature of particles and has profound implications for our understanding of the behavior of matter at the quantum level. At its core, the uncertainty principle states that the more precisely the position of a particle is known, the less precisely its momentum can be determined, and vice versa. This is not due to limitations in our measurement tools or experimental techniques, but rather a fundamental property of quantum systems. In classical mechanics, it is assumed that both position and momentum can be known with arbitrary precision at the same time. However, in quantum mechanics, the act of measuring one of these properties disturbs the system in such a way that the other becomes less predictable. The mathematical expression of Heisenberg's uncertainty principle is given by the inequality delta x delta p greater than or equal to h over 4 pi. The uncertainty in position multiplied by the uncertainty in momentum is greater than or equal to 1/2 of the reduced Planck constant. This inequality shows that the product of the uncertainties in position and momentum is always greater than or equal to a small fixed value. In other words, no matter how precise our measurements of one property are, there will always be a corresponding level of uncertainty in the other property. This principle is not just a result of practical limitations, but a reflection of the intrinsic nature of quantum systems. It arises from the wave-particle duality of matter. In quantum mechanics, particles such as electrons exhibit both particle-like and wave-like properties. The wave function, which describes the quantum state of a particle, represents a probability distribution of possible positions and momenta. The wave nature of particles means that their properties cannot be precisely localized to a single point. Instead, there is a spread of possible positions and momenta, with the uncertainty principle describing the inherent trade-off between the precision of these measurements. The uncertainty principle is best understood when considering the wave-particle duality of electrons. When an electron is confined to a very small region of space, its wave function becomes more spread out in momentum space, meaning its momentum is less certain. Conversely, if the electron's momentum is precisely measured, its wave function is spread out in space, making its position uncertain. The uncertainty principle thus emerges naturally from the wave nature of particles. The act of localizing a particle in space disturbs its momentum, and the act of measuring its momentum disturbs its position. A key consequence of the uncertainty principle is that there are limits to how much we can know about a quantum system. In classical mechanics, we can, in theory, measure position and momentum simultaneously with arbitrary precision, which allows us to predict the future behavior of a system with complete accuracy. In quantum mechanics, however, the uncertainty principle places a fundamental limit on how much information we can extract about a system. This limitation is not just a technical challenge, but a feature of the quantum world itself. The implications of the uncertainty principle are far-reaching, and they challenge our classical intuition about the nature of reality. One of the most profound consequences of the uncertainty principle is that it suggests that at a fundamental level, the universe is probabilistic, not deterministic. In classical mechanics, if we know the position and momentum of an object at one point in time, we can predict its future trajectory with certainty. In contrast, quantum mechanics only allows us to calculate the probabilities of where a particle might be or what momentum it might have. The uncertainty principle captures this inherent uncertainty in the behavior of quantum systems. Heisenberg's uncertainty principle also has important consequences for the concept of measurement in quantum mechanics. In classical physics, measurement is considered an external process that does not affect the system being measured. However, in quantum mechanics, the act of measurement disturbs the system in such a way that it influences the outcome. The uncertainty principle highlights this disturbance. The more precisely we measure one property of a particle, the more we disturb the other property. This is often illustrated using the metaphor of trying to measure the position of a car while it is moving at high speed. If you focus on the position of the car, you lose information about its speed, and vice versa. One of the key insights of the uncertainty principle is that the act of measurement is not a passive process, but an active one that shapes the outcome of the system. This idea is in stark contrast to classical physics, where measurements are assumed to reveal pre-existing properties of the system without altering them. In quantum mechanics, the properties of a system are not definite until they are measured, and the very act of measurement influences the state of the system. The uncertainty principle also challenges our notions of reality itself. If position and momentum cannot both be precisely known at the same time, does this mean that particles do not have definite properties until they are observed? The uncertainty principle suggests that the very act of observing a quantum system plays a crucial role in determining its state. This idea is central to the interpretation of quantum mechanics, and it has led to various philosophical debates about the nature of reality and the role of the observer. Some interpretations, such as the Copenhagen interpretation, argue that the wave function represents the probabilities of different outcomes, and the act of measurement collapses the wave function, resulting in a definite state. Other interpretations, such as the many worlds interpretation, propose that all possible outcomes occur simultaneously in parallel worlds, with the observer's role being less central. In addition to its philosophical implications, Heisenberg's uncertainty principle has practical consequences in a variety of scientific fields. For example, in the study of atomic and subatomic particles, the uncertainty principle places limits on our ability to measure certain properties with high precision. It also plays a role in technologies such as scanning, tunneling microscopes, which rely on the principles of quantum mechanics to create images of surfaces at the atomic level. The uncertainty principle is also crucial in the development of quantum computing, where quantum bits or qubits exploit the probabilistic nature of quantum systems to perform complex calculations that are impossible for classical computers. The uncertainty principle also has implications for our understanding of the universe at the smallest scales. For example, in the study of quantum fields and particles, the uncertainty principle places fundamental limits on the precision with which we can measure certain physical quantities, such as the energy of a particle over short periods of time. This leads to the concept of quantum fluctuations, where particles can spontaneously appear and disappear in empty space, even in a vacuum. These fluctuations are a direct consequence of the uncertainty principle and are thought to play a role in the behavior of the early universe, such as during the period of cosmic inflation that occurred shortly after the Big Bang. Heisenberg's uncertainty principle also influences the development of technologies that rely on quantum mechanics, such as quantum encryption and quantum cryptography. In quantum cryptography, the uncertainty of quantum measurements ensures the security of communication systems, as any attempt to measure the quantum state of a system will disturb it and reveal the presence of an eavesdropper. This provides a level of security that is unattainable in classical communication systems. Wave functions and probability are fundamental concepts in quantum mechanics that describe the behavior and state of quantum systems. In classical physics, objects are described by definite positions, velocities, and trajectories. However, in the quantum world, particles such as electrons do not have definite fixed positions or velocities. Instead, their behavior is described by a mathematical function called the wave function, which encodes information about the probabilities of finding a particle in different states or locations. The wave function is a complex mathematical function that represents the quantum state of a system. It is usually denoted by the Greek letter psi and can be thought of as a probability amplitude. The wave function contains all the information needed to determine the probabilities of various outcomes in a quantum system. Unlike classical particles, quantum particles are described by a spread-out wave rather than a single point in space. The wave function, therefore, provides a way to capture the uncertainty and probabilistic nature of quantum systems. In quantum mechanics, the square of the wave function's magnitude at any given point in space and time gives the probability density of finding a particle in that location. This probability density is sometimes referred to as the probability amplitude of the system. The wave function itself can be thought of as a mathematical tool for determining how likely it is that a particle will be observed in a particular state or position, but it does not provide a definite answer about the outcome of a measurement. Instead, it gives the probabilities for all possible outcomes. To understand this better, consider the analogy of a spinning coin. When the coin is in the air, its state is uncertain, and it can land either heads or tails. However, quantum systems are even more uncertain. A particle, such as an electron, does not have a definite location until it is observed. Before observation, it exists in a superposition of all possible locations, with the wave function describing the probabilities of finding the particle in different places. One key feature of wave functions is that they can describe the superposition of states. This means that a particle can be in multiple states at once, such as being in two places at the same time. However, this does not mean that the particle is physically in both places at once. Rather, it is that there is a probability associated with the particle being in each location. Once a measurement is made, the wave function collapses, and the particle is found in one specific state or location. The wave function is a powerful tool for understanding quantum phenomena. In quantum mechanics, particles do not follow well-defined paths. Instead, their locations and momenta are described by probability distributions, which can be calculated using the wave function. For example, if we want to know the probability of finding an electron in a particular region of space, we would square the wave function at that point. This gives us the probability density, which tells us how likely it is to find the electron in that region. The wave function also plays a crucial role in the evolution of quantum systems. According to the Schrödinger equation, which is the fundamental equation of quantum mechanics, the wave function evolves over time in a deterministic way. This means that, given the initial conditions of a system, the wave function can be used to predict the probabilities of different outcomes at any point in the future. However, once a measurement is made, the wave function collapses and the outcome becomes definite. One of the most important features of wave functions is that they can be used to calculate the probabilities of all possible outcomes in a quantum system. For example, consider an electron in an atom. The electron's wave function will give the probability distribution for the electron's location around the nucleus. The probability density will tell us the likelihood of finding the electron at any particular point in space. In the case of an atom, the electron is more likely to be found in certain regions, such as orbitals, than in others. The wave function is a complex function, meaning that it can have both real and imaginary components. While the wave function itself does not directly correspond to physical quantities like position or momentum, its square, the probability density, gives meaningful information about the likelihood of finding a particle in a particular location. The imaginary part of the wave function plays an essential role in the interference effects observed in quantum systems, such as in the double-slit experiment. In some cases, wave functions can interfere with each other, leading to constructive or destructive interference. Constructive interference occurs when the wave functions combine in such a way that their probabilities reinforce each other, increasing the likelihood of a particular outcome. Destructive interference occurs when the wave functions combine in a way that cancels each other out, reducing the probability of a certain outcome. This interference is a hallmark of quantum systems and has been experimentally observed in phenomena like diffraction and interference patterns. Wave functions also obey the principle of normalization. This means that the total probability of finding a particle somewhere in space must always add up to 1. If the wave function is properly normalized, it ensures that the particle has a 100% chance of being found somewhere in space. In practice, the normalization condition ensures that the probabilities calculated from the wave function are physically meaningful. It is important to note that the wave function represents a probability distribution, not a definitive prediction. In quantum mechanics, the act of measurement plays a critical role in determining the outcome of an experiment. Before measurement, a quantum system is described by a superposition of all possible states, and the wave function gives the probabilities of observing each of those states. After measurement, the wave function collapses, and the system assumes a definite state. The wave function gives us a probabilistic description of the system's behavior, but it cannot provide a precise prediction of the outcome of any individual measurement. The probabilistic nature of quantum mechanics is in stark contrast to classical physics, where objects are assumed to have definite properties such as position and momentum at all times. In classical mechanics, we can predict the exact trajectory of an object if we know its initial conditions. In quantum mechanics, however, we can only calculate the probabilities of different outcomes, and the system's behavior is inherently uncertain. Wave functions are also closely related to the concept of quantum states. A quantum state is a complete description of a quantum system, and the wave function is the mathematical representation of that state. The state of a system can be described by its wave function, which encapsulates all the information about the system's properties, such as energy, position, and momentum. The wave function is a fundamental concept in quantum mechanics because it provides a complete description of the quantum system, allowing us to predict the probabilities of different outcomes. Quantum measurement and wave function collapse are two central concepts in quantum mechanics that challenge our classical understanding of the relationship between observation and the physical world. In classical physics, measurements are seen as passive events that do not influence the system being observed. However, in quantum mechanics, the act of measurement plays an active role in determining the state of a system. This leads to the concept of wave function collapse, which describes how a quantum system, initially in a superposition of multiple possible states, transitions to a single definite state once it is observed. The wave function, a complex mathematical function that describes the quantum state of a system, encodes all the possible outcomes of an experiment. Prior to measurement, a quantum system exists in a superposition, meaning it is in a combination of multiple states simultaneously. For example, an electron in an atom can exist in multiple energy levels at once. When a measurement is made, the wave function collapses, and the system assumes a definite state corresponding to the observed outcome. The notion of wave function collapse arose from the realization that quantum systems behave in fundamentally probabilistic ways. Unlike classical systems, where the properties of an object, such as position or velocity, can be precisely determined, quantum systems only provide probabilities for where a particle might be found or what state it might be in. The wave function gives the probability distribution of possible outcomes, but it does not tell us the exact outcome of a measurement. It is only when an observation is made that the wave function collapses to a single state, and the system is found in one of the possible outcomes described by the wave function. One of the most famous thought experiments that highlights the role of measurement in wave function collapse is Schrödinger's cat, which we will explore later. The essence of this thought experiment is to illustrate the paradoxical nature of quantum mechanics. Before the system is observed, it exists in a superposition of multiple possible states. But once observed, the system collapses into a single, definite state. Schrödinger's cat is simultaneously alive and dead until the box is opened and the state of the cat is observed, at which point it is either alive or dead. This is a striking example of how quantum systems can exist in multiple states at once, and the act of measurement forces them to assume a single state. Quantum measurement is a complex and somewhat mysterious process. In the classical world, measurements reveal pre-existing properties of objects, and the system being observed remains unaffected. However, in quantum mechanics, measurement changes the state of the system being measured. The very act of measuring a quantum system disturbs it in such a way that it causes the wave function to collapse. This collapse is not a gradual process. It is an instantaneous transition from a superposition of possibilities to a single, definite outcome. The nature of this collapse has been the subject of much debate and is a key issue in the interpretation of quantum mechanics. One of the central questions raised by quantum measurement is, what exactly constitutes a measurement? In classical mechanics, measurement is a simple process where a device, such as a thermometer or a ruler, records the value of a property of a system without altering that property. In quantum mechanics, however, the concept of measurement is more complicated. The most straightforward answer is that a measurement involves the interaction of the quantum system with an external device, such as a detector or observer, that forces the system to choose one of the possible outcomes described by the wave function. The system collapses into a specific state when this interaction occurs. However, the precise nature of this collapse remains an open question in the philosophy of quantum mechanics. Several different interpretations have been proposed to explain wave function collapse and the role of measurement. One of the most well-known interpretations is the Copenhagen interpretation, which suggests that the wave function represents the probabilities of various outcomes, and the act of measurement causes the wave function to collapse to a single outcome. According to this view, the wave function is a mathematical tool that encodes our knowledge of the system, and it does not represent an objective reality that exists independently of observation. Another interpretation, known as the many worlds interpretation, takes a radically different approach. According to this view, the wave function does not collapse at all. Instead, all possible outcomes of a quantum measurement actually occur in parallel, each in a separate branch of the universe. In this view, the observer does not cause the wave function to collapse, but rather becomes entangled with the system in such a way that they experience only one of the many possible outcomes. This interpretation removes the need for wave function collapse, but it introduces the idea of multiple parallel universes. There is also the de Broglie-Bohm interpretation, which suggests that the wave function does not collapse, but instead evolves deterministically according to the Schrödinger equation. In this view, particles have well-defined positions at all times, and the wave function guides the motion of particles, even though it is not directly observed. The de Broglie-Bohm theory avoids some of the paradoxes associated with wave function collapse, but it requires a more complex understanding of quantum mechanics. Despite these different interpretations, the Copenhagen interpretation remains the most widely accepted explanation of wave function collapse in mainstream quantum mechanics. In this interpretation, the wave function represents our knowledge of the system, and measurement causes the collapse of the wave function to a definite state. This is the version of quantum mechanics that is taught in most physics courses and is used in most practical applications of quantum mechanics, such as quantum computing and quantum cryptography. One of the key insights of the Copenhagen interpretation is that the wave function represents probabilities, not certainties. Before a measurement is made, the wave function gives us the likelihood of observing a particular outcome, but it does not provide a definitive answer. This probabilistic nature of quantum mechanics is in stark contrast to classical physics, where objects have definite properties that can be measured with arbitrary precision. The concept of wave function collapse also raises important questions about the role of the observer in quantum mechanics. In classical physics, the observer is an external entity that merely records the state of a system without influencing it. In quantum mechanics, however, the observer plays a crucial role in determining the outcome of a measurement. The observer's interaction with the quantum system forces it to collapse into a single state, but this raises questions about the nature of reality itself. Does the universe only choose a definite state when it is observed, or do the different possible states exist in some form even when unobserved? One implication of wave function collapse is that the future behavior of a quantum system is fundamentally uncertain. Unlike classical systems, where the future can be predicted if we know the initial conditions, quantum systems only provide probabilities for future outcomes. Once a measurement is made, the wave function collapses, and the system assumes a definite state. However, before measurement, the system exists in a superposition of multiple possibilities, and its future behavior is not determined. Another important consequence of wave function collapse is that it implies that the act of measurement is not a passive process, but an active one. In classical mechanics, measurements are thought to reveal pre-existing properties of a system. However, in quantum mechanics, the act of measurement plays a crucial role in determining the state of the system. The wave function collapse is a direct result of this interaction between the quantum system and the observer. The Copenhagen and many worlds interpretations are two of the most prominent and debated explanations of quantum mechanics, each offering a distinct perspective on the nature of reality and the role of observation in shaping the quantum world. These interpretations arise from the core principles of quantum mechanics, which involve probabilistic outcomes and wave function collapse. While both interpretations are rooted in the same mathematical framework, they propose different ways of understanding the measurement process and the underlying reality of quantum systems. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, is the traditional and most widely accepted interpretation of quantum mechanics. It posits that the wave function represents the probability distribution of a quantum system's possible states. Before a measurement is made, a quantum system exists in a superposition of all possible states, with the wave function describing the probabilities of these states. Upon measurement, however, the wave function collapses, and the system assumes a definite state corresponding to the observed outcome. In this view, the act of measurement plays a crucial role in determining the state of the system, and the wave function collapse is a direct result of the interaction between the system and the observer. The Copenhagen interpretation is often described as a pragmatic approach to quantum mechanics. It does not offer a detailed explanation of the wave function collapse itself, but instead focuses on the practical implications of measurement. In this interpretation, the wave function is considered a mathematical tool used to calculate the probabilities of different outcomes, rather than a physical entity that describes the true nature of reality. The collapse of the wave function is seen as a process that occurs during measurement, but the exact mechanism is left unspecified. According to this view, the universe exists in a probabilistic state until it is observed, at which point it chooses a definite outcome based on the probabilities encoded in the wave function. One of the key elements of the Copenhagen interpretation is the role of the observer. In classical physics, the observer is an external entity that does not influence the system being measured. However, in the quantum world, the observer plays an active role in determining the state of the system. The process of measurement forces the wave function to collapse, and this collapse is what gives rise to the definite outcome of the measurement. This view has led to various philosophical debates, particularly concerning the nature of reality and the role of consciousness in measurement. Some versions of the Copenhagen interpretation suggest that consciousness is necessary for the collapse of the wave function, while others argue that the collapse is a purely physical process that occurs regardless of observation. In contrast, the many worlds interpretation proposed by Hugh Everett III in 1957 offers a radically different view of quantum mechanics. Rather than invoking wave function collapse, the many worlds interpretation suggests that all possible outcomes of a quantum measurement actually occur, but in separate, non-interacting branches of the universe. According to this interpretation, the wave function never collapses. Instead, it evolves deterministically according to the Schrödinger equation, and each possible outcome of a measurement corresponds to a different world or branch of the universe. In other words, the universe splits into multiple parallel realities, each containing one of the possible outcomes of the quantum measurement. The many worlds interpretation avoids the need for wave function collapse by proposing that all possible outcomes exist simultaneously in different branches of the universe. This means that when a quantum measurement is made, the universe branches into several distinct realities, each corresponding to one of the possible outcomes. For example, if a quantum system has two possible states, A and B, the many worlds interpretation suggests that the universe splits into two branches, one in which the system is in state A and one in which the system is in state B. From the perspective of each observer, only one of these outcomes is experienced, but in the many worlds framework, both outcomes exist in parallel, each in its own separate world. One of the key strengths of the many worlds interpretation is that it provides a deterministic, observer-independent view of quantum mechanics. In this interpretation, there is no need to invoke the collapse of the wave function, and the probabilistic nature of quantum mechanics is explained by the fact that all possible outcomes occur in separate branches of the universe. The evolution of the wave function is governed by the Schrödinger equation, which is deterministic, meaning that the future state of the system is fully determined by its current state. In this view, the role of the observer is not to cause the collapse of the wave function, but to experience one of the many possible outcomes in a particular branch of the universe. The many worlds interpretation also offers a more intuitive way of understanding quantum superposition. In the Copenhagen interpretation, a quantum system exists in a superposition of multiple states, but when measured, it collapses into one of those states. In the many worlds interpretation, however, all of the possible states coexist in parallel universes, and the observer simply perceives one of the outcomes. This interpretation removes the need for wave function collapse and provides a more straightforward way of thinking about the probabilistic nature of quantum systems. Despite its appeal, the many worlds interpretation is not without its challenges. One of the main criticisms of this interpretation is the issue of ontological cost, how to account for the existence of multiple parallel worlds. The many worlds interpretation suggests that there are an infinite number of universes, each containing a different version of reality, but it is unclear how to account for the physical existence of these worlds. The theory also raises questions about how to reconcile the subjective experience of the observer with the objective reality of parallel universes. If all outcomes occur in separate branches of the universe, then why do we experience only one outcome? And how do we explain the apparent splitting of the universe? Furthermore, the many worlds interpretation is often criticized for its lack of empirical testability. Unlike the Copenhagen interpretation, which makes specific predictions about the outcomes of quantum measurements, the many worlds interpretation does not offer a clear way to test its claims. Since the parallel worlds are non-interacting and cannot be observed, it is difficult to design experiments that could confirm or refute the theory. This has led some to argue that the many worlds interpretation is more of a philosophical position than a scientific theory. Despite these challenges, the many worlds interpretation has gained support from a number of physicists who see it as a more elegant and consistent explanation of quantum mechanics. It removes the need for wave function collapse, which is seen as a somewhat mysterious and ad hoc process in the Copenhagen interpretation. Many proponents of the many worlds interpretation argue that it provides a more coherent and deterministic framework for understanding quantum mechanics, with fewer paradoxes and unresolved issues. In contrast, the Copenhagen interpretation is often seen as more pragmatic and practical because it offers a clear and straightforward framework for making predictions about the outcomes of quantum measurements. While it does not provide a complete explanation of the underlying reality of quantum systems, it has been extremely successful in making accurate predictions and has been widely used in experimental physics and quantum technology. Quantum entanglement is one of the most fascinating and puzzling phenomena in quantum mechanics, challenging our classical understanding of how particles interact and how information can be transmitted. Entanglement occurs when two or more particles become so deeply interconnected that the state of one particle is directly related to the state of another, regardless of the distance separating them. This phenomenon suggests that the behavior of particles can be correlated in ways that seem to defy the conventional laws of physics, particularly the speed of light limitation for transmitting information. Quantum entanglement has been described as one of the most non-intuitive aspects of quantum mechanics, and its implications have sparked debate and led to profound philosophical discussions about the nature of reality. At its core, quantum entanglement arises when two or more quantum particles, such as electrons or photons, interact in a way that their individual quantum states cannot be independently described. Instead, the system as a whole must be described by a single wave function. This wave function encompasses all of the possible states of the system, and the entangled particles are considered to be in a shared quantum state. Once entangled, the state of one particle becomes intrinsically linked to the state of the other as, meaning that measuring one particle will instantaneously affect the state of the others, even if they are far apart. This spooky action at a distance, as Albert Einstein famously referred to it, is one of the most paradoxical features of quantum entanglement. One of the key elements of quantum entanglement is that the properties of the entangled particles, such as their spin, polarization, or position, are not independently determined. Instead, the properties of each particle are defined in relation to the other. For example, if two particles are entangled in such a way that they share opposite spins, measuring the spin of one particle will immediately reveal the spin of the other, even if the particles are light years apart. This instantaneous connection between the particles is what makes quantum entanglement so remarkable and mysterious, as it seems to violate the principle of locality, which states that objects can only influence one another through direct interaction or signals, traveling at or below the speed of light. The phenomenon of entanglement was first described by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935 in what is known as the EPR paradox. In this thought experiment, Einstein and his colleagues suggested that if quantum mechanics were correct, then entangled particles would be able to instantaneously affect each other regardless of distance. This seemed to violate the principle of locality and suggested that quantum mechanics might be incomplete. Einstein famously referred to this idea as spooky action at a distance, as he was uncomfortable with the non-locality implied by entanglement. However, in the decades that followed, experimental evidence began to accumulate supporting the existence of quantum entanglement. In the 1960s, physicist John Bell developed a theorem, now known as Bell's theorem, which showed that no local hidden variable theory could explain the correlations between entangled particles. In other words, If quantum mechanics is correct, then the behavior of entangled particles cannot be explained by any classical theory that assumes local interactions. Bell's theorem led to a series of experiments, most notably those conducted by physicist Alain Aspect in the 1980s, that confirmed the predictions of quantum mechanics and demonstrated that entanglement is a real observable phenomenon. One of the most intriguing aspects of quantum entanglement is its apparent violation of causality. In classical physics, it is assumed that information can only travel at or below the speed of light, meaning that no information can be transmitted faster than light. However, in the case of entangled particles, the measurement of one particle seems to instantaneously affect the state of the other, regardless of the distance between them. This suggests that the conventional understanding of space and time, as described by special relativity, might not fully apply at the quantum level. While no information is actually transmitted faster than light, since the measurement outcomes are random, the correlation between the entangled particles appears to be instantaneous, leading to a profound rethinking of the nature of space, time, and causality. Quantum entanglement has practical implications beyond its philosophical implications. In recent years, entanglement has become a central resource in the emerging field of quantum information science, which seeks to harness the strange properties of quantum systems to develop new technologies such as quantum computing and quantum cryptography. Quantum computers, which exploit the principles of superposition and entanglement, have the potential to solve certain problems much more efficiently than classical computers. By creating and manipulating entangled states of qubits, quantum bits, quantum computers could perform computations that would be infeasible for classical machines. For example, quantum computers could be used to break certain types of encryption, simulate complex quantum systems, or optimize large-scale problems in fields such as logistics and artificial intelligence. Quantum entanglement also plays a key role in quantum cryptography, particularly in protocols such as quantum key distribution, QKD. In QKD, entangled particles are used to securely exchange encryption keys between two parties. The security of this system relies on the fact that any attempt to eavesdrop on the entangled particles will disturb their quantum state, alerting the parties to the presence of an intruder. This property of entanglement makes quantum cryptography a potentially unbreakable method of securing communications, as any interference with the entangled particles would be immediately detectable. Despite its many applications, quantum entanglement continues to challenge our understanding of the physical world. One of the main philosophical questions raised by entanglement is the nature of reality itself. In classical physics, objects are assumed to have definite properties that can be measured independently of observation. However, in quantum mechanics, the properties of entangled particles are not defined until they are measured, and the act of measurement seems to influence the system. This raises the question of whether the properties of a quantum system are intrinsic to the system or whether they depend on the observer. The fact that entangled particles can instantaneously influence each other, regardless of distance, suggests that quantum mechanics is not simply a local theory, but one that involves a deep interconnectedness between particles that transcends the classical understanding of space and time. This has led to various interpretations of quantum mechanics that attempt to explain the role of entanglement in the context of the broader nature of reality. The Copenhagen interpretation, for example, suggests that the wave function of a quantum system encodes all of the possible outcomes of a measurement, and the act of measurement causes the wave function to collapse into a single state. In this view, entanglement is a result of the interdependence of particles in a quantum system, and the correlations between entangled particles are explained by the collapse of the wave function upon measurement. The many worlds interpretation, on the other hand, suggests that all possible outcomes of a quantum measurement occur in parallel, with each outcome corresponding to a separate branch of the universe. In this view, entanglement is not a mysterious, non-local phenomenon, but rather a reflection of the fact that all possible outcomes exist simultaneously in different worlds. This interpretation avoids the need for wave function collapse and provides a more deterministic view of quantum mechanics. But it introduces the idea of parallel universes, which remains a subject of debate. Another interpretation, known as the de Broglie-Bohm theory, proposes that particles have well-defined positions at all times, and the wave function guides their motion. In this view, entanglement is explained by the fact that the particles are connected through the wave function, which evolves deterministically according to the Schrödinger equation. This theory removes the need for wave function collapse and offers a more classical view of reality, but it requires a more complex understanding of quantum mechanics. Bell's theorem and the concept of non-locality are central to the foundations of quantum mechanics and have profound implications for our understanding of reality. Bell's theorem, formulated by physicist John Bell in 1964, showed that no local hidden variable theory can explain the correlations observed in quantum entanglement experiments. The theorem provided a clear and rigorous mathematical framework for understanding the nature of quantum mechanics and its apparent departure from classical notions of causality and locality. Non-locality, which refers to the idea that particles can instantaneously influence one another over long distances, lies at the heart of quantum mechanics and is directly related to Bell's theorem. The implications of these concepts have sparked debates about the nature of reality, the limits of human knowledge, and the potential for new technologies based on quantum entanglement. Bell's theorem is a result of his attempts to address the paradox raised by quantum entanglement, which seemed to defy the principles of classical physics. In classical physics, it was assumed that particles had definite properties that could be measured independently of observation, and that interactions between objects occurred locally, meaning that information could only travel at or below the speed of light. Quantum mechanics, however, introduced the idea that particles could become entangled, meaning that their properties were correlated in such a way that the measurement of one particle would instantly affect the state of another, even if they were far apart. This spooky action at a distance raised serious concerns for physicists, including Albert Einstein, who famously rejected the idea of non-locality and believed that quantum mechanics was incomplete. To resolve the paradox, Bell developed a theorem that showed that any local hidden variable theory, that is, a theory in which particles have definite properties determined by hidden variables and interactions occur locally, could not account for the observed correlations between entangled particles. Bell's theorem demonstrated that the predictions of quantum mechanics and local hidden variable theories were fundamentally different, and that experiments designed to test these predictions could distinguish between the two. If the results of these experiments were consistent with quantum mechanics, then it would mean that the correlations between entangled particles could not be explained by any local theory. Bell's theorem is based on the idea of Bell inequalities, which are mathematical inequalities that local hidden variable theories must satisfy. Quantum mechanics, however, predicts that the correlations between entangled particles will violate these inequalities, which means that the outcomes of certain measurements will be more strongly correlated than would be possible under a local hidden variable theory. Bell's theorem thus provides a way to test the validity of quantum mechanics versus local realism, which is the idea that objects have definite properties and that interactions are local. In 1964, Bell showed that, in principle, experiments could be performed to test his theorem. These experiments would measure the correlations between entangled particles, such as photons or electrons, under different conditions. If the measurements violated the Bell inequalities, it would provide evidence that quantum mechanics was correct and that local hidden variable theories were not sufficient to explain the observed results. If the measurements were consistent with local realism, it would suggest that quantum mechanics was incomplete or that there was some hidden variable theory that could account for the correlations. The first experimental tests of Bell's theorem were conducted in the 1970s and 1980s by physicists such as Alain Aspect. These experiments involved entangled photons and measured the correlations between their polarization or other properties. The results consistently showed violations of the Bell inequalities, providing strong experimental evidence in favor of quantum mechanics and against local hidden variable theories. The experiments confirmed that the correlations observed in quantum entanglement experiments could not be explained by any local theory, and that the quantum world was fundamentally non-local. Non-locality, as revealed by Bell's theorem, is one of the most surprising and counterintuitive aspects of quantum mechanics. In classical physics, objects are assumed to have definite properties, such as position or velocity, that can be measured independently of one another. These properties are assumed to be localized in space and time, meaning that objects only interact with one another if they are in close proximity, and information can only travel at or below the speed of light. Quantum mechanics, however, suggests that particles can be entangled in such a way that their properties are correlated, even when they are separated by vast distances. This instantaneous correlation between distant particles is what is referred to as non-locality. Non-locality in quantum mechanics does not mean that information can be transmitted faster than light. Instead, it means that the properties of entangled particles are not independently determined, but are instead linked in such a way that the state of one particle is instantaneously connected to the state of the other, no matter how far apart they are. When a measurement is made on one particle, the state of the other particle is immediately determined, even if the two particles are light years apart. This apparent violation of the speed of light limit led to the notion of spooky action at a distance, which Einstein found troubling. However, quantum mechanics does not allow for faster than light communication, as the outcomes of measurements are random and cannot be controlled by an observer. The concept of non-locality is central to the philosophical debates surrounding the interpretation of quantum mechanics. If particles can be instantaneously connected in this way, then it raises questions about the nature of space and time. Are space and time fundamental features of reality, or are they emergent properties of a deeper non-local structure? Some interpretations of quantum mechanics, such as the Copenhagen interpretation, simply accept non-locality as an intrinsic feature of the quantum world. Others, such as the many worlds interpretation, offer alternative explanations for the strange correlations observed in quantum experiments. Despite the different interpretations, however, the violation of Bell inequalities and the phenomenon of non-locality remains central to our understanding of quantum mechanics. Bell's theorem and non-locality have far-reaching implications for our understanding of the nature of reality. One of the key consequences of non-locality is that it challenges the classical notion of causality. In classical physics, the cause of an event is assumed to be located at a specific point in space and time, and the effect of that event is transmitted locally. In quantum mechanics, however, the effects of one particle's state can be instantaneously transmitted to another, regardless of distance. This suggests that the causal structure of the universe may be more complex and interconnected than previously thought. The violation of Bell inequalities and the demonstration of non-locality have prompted physicists and philosophers to reconsider the nature of causality, the role of the observer, and the relationship between space, time, and reality. Bell's theorem also plays a critical role in the development of quantum technologies. The principles of quantum mechanics, including non-locality, are now being harnessed to create new technologies such as quantum computers and quantum cryptography. Quantum computers, which rely on the entanglement and superposition of quantum bits, qubits, could revolutionize fields such as computation, cryptography, and artificial intelligence. Quantum cryptography, which uses the principles of quantum mechanics to securely transmit information, relies on the concept of entanglement and the violation of Bell inequalities to ensure that any attempt to eavesdrop on a quantum communication would be detectable. The non-locality revealed by Bell's theorem is therefore not just a theoretical curiosity, but a crucial resource for developing practical applications in the field of quantum technology. Quantum teleportation is one of the most fascinating and mind-bending phenomena in quantum mechanics. It is a process that allows the state of a quantum system to be transferred from one location to another, without physically moving the particle itself. Although the term teleportation may evoke images of science fiction, quantum teleportation is a real and experimentally verified phenomenon that takes advantage of the strange properties of quantum entanglement and the fundamental principles of quantum mechanics. It does not involve the transportation of matter, but rather the transfer of information encoded in the quantum state of a particle. Quantum teleportation has profound implications for fields such as quantum computing, quantum communication, and quantum cryptography, offering the potential for secure, instantaneous communication over long distances. At the heart of quantum teleportation is the concept of quantum entanglement. As discussed earlier, entanglement is a phenomenon where two or more particles become correlated in such a way that their properties are linked regardless of the distance between them. Once two particles are entangled, the measurement of one particle's state instantaneously determines the state of the other. even if the particles are separated by vast distances. Quantum teleportation relies on this deep connection between entangled particles to transmit the state of a particle from one location to another, without the need for physical transportation. Quantum teleportation involves several key steps. First, an entangled pair of particles, typically photons or atoms, are created. These particles are entangled in such a way that their quantum states are strongly correlated, meaning that their properties, such as spin, polarization, or position, are connected even when they are separated by large distances. Then, a joint measurement, known as a Bell state measurement, is performed on the particle whose state is to be teleported, referred to as the sender particle, and one of the entangled particles. This measurement effectively mixes the two particles' quantum states, providing information about the relative quantum state of the sender particle in relation to the entangled particle. Following the measurement, classical information about the measurement result must be sent from the sender to the receiver. This classical communication, which happens at the speed of light, provides the necessary information for the receiver to reconstruct the quantum state of the sender particle. Finally, the receiver, who has the second entangled particle, uses the classical information received from the sender to apply a specific transformation to their particle. This transformation allows the receiver to recreate the quantum state of the sender particle. At this point, the state of the sender particle has been effectively teleported to the receiver, and the original particle no longer holds the information that it did before the teleportation process. It is important to note that while the quantum state of the sender particle has been successfully transmitted to the receiver, the particle itself is not physically transported. The sender particle's original state is destroyed during the Bell state measurement, and the receiver's particle assumes this state in its place. This is a key feature of quantum teleportation. It is not the particle that is moved, but the quantum information encoded in that particle state. Quantum teleportation is a direct consequence of the principles of quantum mechanics and relies on the entanglement of particles. However, it is important to recognize that quantum teleportation does not violate the theory of relativity. In particular, the process does not involve faster-than-light communication, since the classical information needed to complete the process still has to be transmitted at the speed of light. The transfer of quantum information is instant, but it is not a form of communication that allows for the transmission of information faster than light. This means that quantum teleportation does not violate causality or the speed of light limit, despite its seemingly spooky nature. The idea of quantum teleportation was first proposed in 1993 by physicists Charles Bennett, Gilles Brassard, and others. They showed that it was possible to teleport a quantum state by using entanglement and classical communication. This groundbreaking work demonstrated that quantum teleportation was not just a theoretical possibility, but a practical process that could be experimentally realized. Since then, quantum teleportation has been experimentally verified in a variety of settings, using entangled photons and other quantum systems. One of the earliest successful demonstrations of quantum teleportation was conducted in 1998 by a team of physicists at the University of Innsbruck, Austria. The experiment involved teleporting the quantum state of a photon using entangled photons, and the results confirmed the theoretical predictions of quantum teleportation. Since then, many other experiments have been conducted, demonstrating the teleportation of quantum states over increasingly long distances and with different types of particles. While the concept of teleporting matter, as seen in science fiction, remains far from realization, the teleportation of quantum states has profound implications for the development of quantum technologies. One of the most exciting potential applications of quantum teleportation is in the field of quantum communication. In quantum communication, the goal is to transmit quantum information securely and efficiently over long distances. Quantum teleportation offers a way to transfer quantum information without the need for a physical medium to carry the information. This could lead to the development of ultra-secure communication networks, where the information is encoded in quantum states and transmitted between distant locations using entanglement and teleportation. Quantum teleportation is also an essential component of the emerging field of quantum computing. Quantum computers rely on the principles of superposition and entanglement to process information in ways that classical computers cannot. The ability to teleport quantum states between quantum computers could enable the creation of distributed quantum networks, where quantum information is shared and processed across different machines. This could lead to the development of powerful quantum algorithms that can solve problems beyond the capabilities of classical computers. Furthermore, quantum teleportation has important implications for the field of quantum cryptography. In quantum cryptography, the security of communication is guaranteed by the principles of quantum mechanics, such as the no-cloning theorem and the fact that measurements disturb quantum states. Quantum teleportation could be used in protocols such as quantum key distribution, QKD, where entangled particles are used to securely share encryption keys between distant parties. The transfer of quantum states via teleportation could enhance the security of these protocols by providing a way to transmit quantum information without exposing it to eavesdropping. Despite its promise, quantum teleportation faces several challenges that need to be overcome before it can be fully utilized in practical applications. One of the main challenges is the difficulty of maintaining quantum entanglement over long distances. Entangled particles are extremely delicate and can easily become decoherent due to interactions with their environment. In order for quantum teleportation to be practical for long-distance communication, researchers must develop methods for preserving entanglement and minimizing the effects of decoherence. Another challenge is the need for efficient and reliable methods of creating and manipulating entangled particles. Current techniques for generating entangled particles are still relatively slow and require precise control. As quantum technologies continue to advance, researchers are working on improving these techniques to make quantum teleportation more scalable and feasible for real-world applications. Quantum field theory, QFT, is a fundamental framework in theoretical physics that combines quantum mechanics with special relativity to describe the behavior of fundamental particles and their interactions. It represents a deep and powerful understanding of the universe at the most elementary level, where fields, rather than particles, are the basic building blocks of nature. In quantum field theory, particles are seen as excitations or quanta of underlying fields which permeate all of space. This theory not only explains the forces that govern the interactions between particles, but also underpins the most successful physical theories in modern physics, including the Standard Model of particle physics. At its core, QFT is an extension of quantum mechanics that replaces the classical concept of a particle as a point-like object, with the idea of fields that extend throughout space and time. These fields are dynamic and can interact with one another in various ways. A particle is no longer just an isolated entity, but rather a localized excitation of a quantum field. Each type of particle corresponds to a specific type of field, such as the electromagnetic field for photons, the Higgs field for the Higgs boson, and the electron field for electrons. These fields exist throughout the entire universe, and their interactions are governed by quantum principles. In QFT, space and time are treated as a continuous, four-dimensional fabric that combines the three dimensions of space with time, creating a four-dimensional space-time. This treatment of space-time allows for the incorporation of special relativity, ensuring that QFT is consistent with the theory that describes how objects move through space and time at high velocities. The theory also provides a framework for understanding the way particles interact by exchanging force-carrying particles, known as gauge bosons. These bosons mediate the fundamental forces of nature, such as the electromagnetic force, the weak nuclear force, and the strong nuclear force. One of the central principles of QFT is that every particle is associated with a specific field that governs its behavior. These fields can be thought of as the background against which particles move and interact. For example, the electromagnetic field is responsible for the interactions between electrically charged particles. A photon, the particle associated with light, is simply an excitation of the electromagnetic field. Similarly, the gravitational field is described in general relativity, and in QFT, the graviton is thought to be the particle associated with the force of gravity. Although this remains a theoretical concept, as a full quantum theory of gravity has not yet been developed. The interactions between different fields are governed by the principles of quantum mechanics. This means that the behavior of these fields is probabilistic rather than deterministic. Particles are not fixed objects with definite positions and momenta. Instead, they exist as wave-like excitations within their respective fields, with their properties being described by wave functions. These wave functions provide the probability distributions for where a particle might be found and how it will behave. This probabilistic nature of particles is one of the defining features of quantum mechanics and is a key component of QFT. In quantum field theory, particles can be created or annihilated during interactions. This is a direct consequence of the idea that particles are excitations in fields. When particles collide, they can exchange energy, which may result in the creation of new particles or the annihilation of existing ones. This is a fundamental aspect of particle interactions and is crucial to understanding processes such as particle collisions in high-energy physics experiments, including those conducted at particle accelerators like the Large Hadron Collider. For example, in a high-energy collision, two photons can interact and produce an electron and a positron, demonstrating the creation of matter from energy. In accordance with Einstein's famous equation, energy equals mass times the speed of light squared. Another key feature of QFT is the concept of vacuum fluctuations. The vacuum in quantum field theory is not an empty void, but rather a seething, dynamic space filled with fluctuating quantum fields. Even in the absence of particles, these fields are in a constant state of motion, with virtual particles popping in and out of existence. These virtual particles are temporary fluctuations that arise due to the uncertainty principle of quantum mechanics. Although they cannot be directly observed, their effects can be measured, and they play a crucial role in phenomena like the Casimir effect, which arises from the interaction between the quantum vacuum and objects placed in close proximity to one another. One of the most successful applications of QFT is the development of the Standard Model of particle physics. The Standard Model is a theory that describes the electromagnetic, weak and strong nuclear forces, as well as the fundamental particles that make up matter, such as quarks and leptons. These particles interact with each other through the exchange of force-carrying particles known as gauge bosons. For example, the electromagnetic force is mediated by the photon, the weak force is mediated by the W and Z bosons, and the strong force is mediated by gluons. The Higgs boson, discovered in 2012 at the Large Hadron Collider, is associated with the Higgs field, which is responsible for giving particles their mass. The Standard Model has been incredibly successful in explaining a wide range of experimental observations and has been confirmed by numerous experiments. However, there are still unresolved questions in physics that remain beyond the scope of the Standard Model, such as the nature of dark matter, dark energy, and the gravitational force. In order to address these questions, physicists are working on extending QFT to include a quantum theory of gravity, which would merge quantum mechanics with general relativity. This is an ongoing area of research, and it is hoped that a unified theory, often referred to as a theory of everything, will eventually provide a complete description of the fundamental forces of nature. QFT has also led to the development of powerful computational techniques used to model the behavior of particles and fields in various physical systems. These techniques, such as perturbation theory and lattice quantum field theory, allow physicists to make predictions and simulate complex interactions that cannot be solved exactly. For example, lattice QFT involves discretizing space-time into a grid and solving the equations of QFT numerically. This approach has been used to study quantum chromodynamics, QCD, the theory of the strong force, and has provided valuable insights into the behavior of quarks and gluons. In addition to its applications in particle physics, QFT has found important applications in other areas of physics, including condensed matter physics and cosmology. In condensed matter physics, QFT is used to describe the behavior of electrons and other particles in solids and liquids, providing insights into phenomena like superconductivity and the quantum Hall effect. In cosmology, QFT is used to model the early universe, including the process of cosmic inflation, which is thought to have occurred during the first moments after the Big Bang. Despite its successes, quantum field theory is not without its challenges. The theory can be mathematically complex, involving intricate calculations and the need for regularization techniques to deal with infinities that arise in certain calculations. Moreover, the integration of quantum mechanics with general relativity, especially in the context of gravity, remains an unsolved problem in physics. The search for a quantum theory of gravity continues to be one of the most active areas of research in theoretical physics. Virtual particles and vacuum fluctuations are fundamental concepts in quantum field theory, QFT, which, as we discussed, treats particles as excitations of underlying fields that permeate all of space. While we previously explored how QFT represents the dynamic behavior of these fields, virtual particles and vacuum fluctuations give us a more detailed view of the constant activity happening even in what we might think of as empty space. In classical physics, the vacuum was traditionally seen as a void, a space completely devoid of matter or energy. However, within the framework of QFT, this notion is radically altered. The vacuum is far from empty. Instead, it is a dynamic, fluctuating medium filled with quantum fields that are in constant motion. These fields fluctuate even when no real particles are present, and these fluctuations are at the heart of virtual particles. Virtual particles are short-lived, transient particles that appear and disappear within the quantum vacuum due to these fluctuations. They are called virtual because they do not behave like real particles, which are observable and detectable. Real particles have definite properties, such as position, momentum, and energy, and they can interact with other real particles. Virtual particles, in contrast, exist for an extremely short time and cannot be directly observed. They are, however, an essential part of particle interactions, influencing how particles interact with each other. The creation of virtual particles is made possible by the uncertainty principle, which states that certain pairs of quantities like energy and time cannot be precisely measured simultaneously. This principle allows for temporary violations of conservation laws, as long as these violations are brief enough to avoid detection. In other words, energy can borrow from the vacuum for a very short time to create a pair of virtual particles, one particle and one antiparticle. These particles exist briefly before they annihilate each other and return the borrowed energy to the vacuum, effectively repaid within the limits set by the uncertainty principle. The interaction between real particles often involves the exchange of virtual particles. For instance, in electromagnetic interactions, real charged particles such as electrons interact by exchanging virtual photons, the force carriers of the electromagnetic field. This exchange is responsible for the attractive or repulsive forces between charged particles. Similarly, in the strong and weak nuclear forces, real particles interact by exchanging virtual gluons and WZ bosons, respectively. These virtual particles mediate the fundamental forces in a way that does not require the particles to be directly observable. Thus, virtual particles are central to how forces are transmitted between particles, even though they are not part of the physical objects we can measure directly. Vacuum fluctuations, the continuous variations in energy within the vacuum, are the source of virtual particles. The vacuum in quantum field theory is not empty. It is teeming with these fluctuations, where energy momentarily fluctuates in and out of existence. These fluctuations are an inherent aspect of quantum fields, and although they cannot be observed directly, their presence can be inferred through the phenomena they produce. Essentially, vacuum fluctuations describe the background activity of space, where fields are never completely still, but instead exhibit constant motion. This behavior of the quantum vacuum leads to the creation of virtual particles, which can briefly appear as excitations of these fluctuating fields. One well-known example of the effects of vacuum fluctuations is the Casimir effect. This phenomenon occurs when two closely spaced, uncharged metal plates are placed in a vacuum. The quantum vacuum fluctuations exert a pressure on the plates, which results in a force that pushes them together. This force is a manifestation of the virtual particles that are constantly being created and annihilated in the vacuum. When the plates are placed very close together, the number of virtual particles between them is reduced compared to the surrounding space, leading to a net attractive force. The Casimir effect is a clear demonstration of how quantum fluctuations, despite originating in what seems to be an empty vacuum, can have real and measurable consequences. Another interesting consequence of vacuum fluctuations is Hawking radiation, a phenomenon that occurs near black holes. According to the theory of quantum mechanics, vacuum fluctuations near the event horizon of a black hole can lead to the creation of virtual particle pairs. In these cases, one of the virtual particles may be pulled into the black hole, while the other escapes. The particle that escapes is observed as radiation emitted by the black hole. This radiation carries away energy from the black hole, leading to its gradual loss of mass over time. Hawking radiation is a theoretical prediction that has yet to be directly observed, but provides important insights into the relationship between quantum mechanics and gravity. Virtual particles and vacuum fluctuations are also integral to our understanding of the forces between particles. In quantum field theory, particles interact by exchanging virtual particles, and these interactions define the fundamental forces of nature. The electromagnetic force, for instance, is mediated by virtual photons, while the strong force is mediated by virtual gluons. These virtual exchanges are essential for understanding the behavior of particles at the quantum level, especially in high-energy environments such as particle accelerators, where virtual particles play a key role in the outcomes of particle collisions. The concept of vacuum fluctuations in virtual particles also plays a role in renormalization, a process used in QFT to eliminate infinities that arise in certain calculations. When calculating particle interactions, certain integrals can lead to infinite values. Renormalization is the mathematical procedure used to cancel out these infinities, making the calculations finite and physically meaningful. Virtual particles are part of this process, as they contribute to the energy of the system and influence the renormalization procedure. By adjusting the parameters of the quantum fields involved, physicists can ensure that their predictions remain consistent with experimental observations. In the context of the early universe, vacuum fluctuations would have been especially important during the process of cosmic inflation, which occurred shortly after the Big Bang. The universe underwent a rapid expansion, stretching the quantum fields and causing fluctuations in these fields to be frozen into the fabric of space-time. These primordial fluctuations seeded the formation of galaxies, clusters of galaxies, and large-scale structures in the universe. The imprint of these early vacuum fluctuations is still observable today in the cosmic microwave background radiation, providing a snapshot of the universe when it was just 380,000 years old. The Higgs boson and the origin of mass are central topics in the field of particle physics, particularly in the context of the Standard Model, which is the theoretical framework that describes the fundamental particles and their interactions. The discovery of the Higgs boson in 2012 provided a key piece of evidence for one of the most important and long-standing questions in physics: how do particles acquire mass? The Higgs boson is not just another particle, It is the manifestation of the Higgs field, a fundamental component of the universe that plays a crucial role in shaping the physical world as we know it. Before the discovery of the Higgs boson, the idea of how particles acquire mass was largely theoretical, based on the Standard Model structure. The Standard Model describes the electromagnetic, weak, and strong nuclear forces, as well as the particles that interact with these forces. However, it had a crucial missing element, an explanation for how elementary particles acquire mass. In the Standard Model, particles are predicted to be massless unless they interact with a specific field that bestows mass upon them. This field is the Higgs field, and the particle associated with it is the Higgs boson. The Higgs mechanism, which explains how particles acquire mass, was proposed in the 1960s by physicist Peter Higgs and several other researchers. According to this mechanism, the Higgs field permeates all of space, and particles that interact with this field gain mass. The strength of the interaction between a particle and the Higgs field determines the particle's mass. Some particles, such as the photon, do not interact with the Higgs field at all, which is why they remain massless. Other particles, such as the W and Z bosons, interact strongly with the Higgs field, which is why they are much heavier. To understand how this works, imagine the Higgs field as a sort of invisible molasses that fills the entire universe. Particles moving through this field experience a kind of drag that slows them down, and the more they interact with the Higgs field, the heavier they become. The stronger the interaction, the more mass the particle gains. Particles like electrons interact moderately with the Higgs field, while heavier particles like the top quark interact more strongly, giving them greater mass. The Higgs boson itself is the quantum excitation of this field, meaning that it is the particle that manifests when the Higgs field is disturbed or excited in certain ways. In the years following the proposal of the Higgs mechanism, scientists worked tirelessly to confirm its existence. The Higgs field is not something that can be directly observed, but its effects can be inferred by studying the behavior of particles. The Higgs boson, being the particle associated with the Higgs field, serves as a tangible signal of the field's presence. Finding the Higgs boson would provide experimental confirmation of the Higgs mechanism and, by extension, our understanding of how particles acquire mass. The search for the Higgs boson culminated in 2012 at CERN, the European Organization for Nuclear Research, with the Large Hadron Collider, the world's most powerful particle accelerator. After years of experiments and data collection, scientists at CERN announced the discovery of a particle consistent with the properties of the Higgs boson. This discovery was a monumental achievement in physics, confirming that the Higgs mechanism is indeed responsible for giving particles mass. The discovery also completed the Standard Model of particle physics, providing the final missing piece of the puzzle. The Higgs boson is an incredibly short-lived particle, decaying almost instantly after it is produced in high-energy collisions. Detecting it requires sophisticated detectors capable of tracking the decay products and reconstructing the properties of the original particle. The discovery of the Higgs boson was made possible by the immense energy provided by the LHC, which allowed scientists to probe the very high energy regime where the Higgs boson could be created. One of the most important aspects of the Higgs boson is its role in the Standard Model's explanation of the origin of mass. Mass is a fundamental property of matter that determines how particles interact with each other and with forces. It also plays a crucial role in the formation of atoms and, ultimately, in the structure of matter itself. Without the Higgs mechanism, particles would remain massless, and the universe as we know it would not exist. For instance, the W and Z bosons, which mediate the weak nuclear force, are essential for processes like nuclear fusion and radioactivity. Without mass, these particles would not behave in the way they do, and the forces governing the universe would be fundamentally different. The Higgs mechanism also has profound implications for our understanding of the early universe. Shortly after the Big Bang, the universe was in a hot, dense state, and the Higgs field was in a highly excited state. As the universe expanded and cooled, the Higgs field underwent a phase transition, and particles began to interact with the field and acquire mass. This process helped shape the structure of the universe, leading to the formation of galaxies, stars, and planets. The Higgs field played a crucial role in this process by allowing particles to acquire mass, which in turn allowed matter to clump together and form the objects we observe in the cosmos today. While the Higgs boson confirmed the existence of the Higgs field, there is still much we do not know about this fundamental component of nature. For instance, the exact nature of the Higgs field is still a subject of active research. It is also unclear whether the Higgs mechanism is the only way for particles to acquire mass, or if there are other unknown mechanisms that might contribute to mass. The discovery of the Higgs boson has opened up new avenues for exploration in theoretical physics, particularly in the search for physics beyond the Standard Model. In addition to its role in the Standard Model, the Higgs boson also has important implications for understanding the fundamental forces of nature. The Higgs field interacts with the electromagnetic and weak nuclear forces, which are both part of the electroweak force, a unified theory of the electromagnetic and weak forces. The Higgs mechanism helps explain why the weak nuclear force is so much weaker than the electromagnetic force, a mystery that has puzzled physicists for decades. The discovery of the Higgs boson has also provided new insights into the unification of forces, particularly the search for a grand unified theory, GUT, that could explain how the electromagnetic, weak, and strong forces are related. Quantum computing represents a revolutionary approach to computation, harnessing the principles of quantum mechanics to perform calculations in ways that classical computers cannot. While classical computers process information using binary bits, which exist in one of two possible states, 0 or 1, quantum computers use quantum bits, or qubits, which have properties that allow them to exist in multiple states simultaneously. This fundamental difference gives quantum computers the potential to solve certain problems exponentially faster than classical computers, making them a powerful tool for a wide range of applications, from cryptography to materials science. At the heart of quantum computing are qubits, which are the quantum counterparts of classical bits. Unlike classical bits, which are discrete and can only be in one state at a time, either 0 or 1, qubits can exist in a superposition of states. A qubit is represented by a quantum state, which can be a combination of both 0 and 1, with certain probabilities associated with each state. This phenomenon is known as superposition. The ability of qubits to be in multiple states at once allows quantum computers to perform parallel computations, potentially solving problems much more efficiently than classical computers. Superposition is one of the key principles of quantum mechanics that makes quantum computing so powerful. In a classical computer, to perform a calculation, the computer must process each possible state one at a time. In contrast, a quantum computer can explore many possible states simultaneously due to the superposition of qubits. For example, with just 2 qubits, a quantum computer can represent all 4 possible states, 0, 0, 0, 1, 1, 0, and 1, 1, at once. As the number of qubits increases, the number of states that can be represented simultaneously grows exponentially. With n qubits, a quantum computer can represent 2 raised to the power of n states at once, making quantum computers particularly suited for solving problems with large data sets or complex calculations. While superposition allows quantum computers to process vast amounts of information in parallel, another crucial property of qubits is entanglement. Entanglement is a quantum phenomenon in which the states of 2 or more qubits become linked, such that the state of one qubit cannot be described independently of the state of the others, even if they are separated by large distances. When qubits become entangled, the information about their states is shared in a way that allows them to influence each other instantaneously, regardless of the distance between them. This property can be used to enhance the computational power of quantum computers, enabling them to perform tasks that would be infeasible for classical computers. Quantum entanglement has profound implications for quantum computing. By entangling qubits, quantum computers can perform more complex operations in less time. The entanglement of qubits can be used to create quantum gates, which are the building blocks of quantum algorithms. These quantum gates manipulate the states of qubits in ways that enable quantum computers to solve problems that would take classical computers an impractically long time to solve. For example, quantum computers have been shown to be potentially capable of factoring large numbers exponentially faster than classical computers, which has significant implications for cryptography. Despite the immense potential of quantum computing, building a functional quantum computer is an incredibly difficult task. Qubits are highly sensitive to their environment, and even the slightest disturbance can cause them to lose their quantum properties in a process known as decoherence. This makes it challenging to maintain the superposition and entanglement of qubits long enough to perform meaningful computations. To address this, researchers are developing various techniques to isolate qubits from external noise and control their interactions with precision. This includes using superconducting circuits, trapped ions, and other advanced technologies to create and manipulate qubits. Another challenge in quantum computing is the issue of error correction. Due to the fragile nature of qubits, quantum computations are prone to errors, and traditional error correction methods used in classical computing do not work for quantum systems. Quantum error correction is an active area of research, with several strategies being explored to protect qubits from errors and maintain the integrity of quantum computations. One promising approach is the use of redundant encoding, where the information in a qubit is spread across multiple qubits to reduce the impact of errors. However, error correction in quantum computing requires a large overhead as many physical qubits are needed to protect a single logical qubit. Despite these challenges, significant progress has been made in the development of quantum computers. In recent years, several companies and research institutions have successfully demonstrated small-scale quantum computers with a limited number of qubits. These early quantum computers have been used to perform proof-of-concept experiments and solve simple problems that would be difficult for classical computers. As quantum computing technology continues to improve, it is expected that quantum computers will be able to tackle more complex problems and achieve breakthroughs in fields such as optimization, machine learning, and drug discovery. One of the most famous examples of a quantum algorithm is Shor's algorithm, which can factor large numbers exponentially faster than the best-known classical algorithms. The ability to factor large numbers efficiently has profound implications for cryptography, particularly for public key encryption systems that rely on the difficulty of factoring large numbers. If large-scale quantum computers can be built, they could potentially break many of the cryptographic systems currently in use. This has led to the development of quantum-safe cryptography, which aims to create encryption methods that are resistant to quantum attacks. Another important quantum algorithm is Grover's algorithm, which provides a quadratic speedup for searching unsorted databases. While Grover's algorithm does not offer the same exponential speedup as Shor's algorithm, it still represents a significant improvement over classical algorithms, particularly for tasks that involve searching large data sets. Grover's algorithm has potential applications in fields such as artificial intelligence, optimization, and data analysis. Quantum computing also holds promise for solving complex problems in materials science and chemistry. For example, quantum computers can be used to simulate the behavior of molecules at the quantum level, which is a task that is extremely difficult for classical computers. This could lead to breakthroughs in the development of new materials, drugs, and chemical processes. Quantum simulations could allow researchers to explore the properties of materials with unprecedented accuracy, potentially leading to the discovery of new materials with unique properties or more efficient chemical reactions. The potential applications of quantum computing are vast and varied, and the field is still in its infancy. While current quantum computers are limited in terms of the number of qubits and the complexity of the problems they can solve, the pace of progress is accelerating. As the technology matures, quantum computers are expected to revolutionize fields such as cryptography, artificial intelligence, material science, and optimization. However, there is still much work to be done before large-scale, fault-tolerant quantum computers become a reality. Superposition and entanglement are two fundamental concepts in quantum mechanics that play a crucial role in quantum computation. These properties allow quantum computers to perform calculations in ways that classical computers cannot, potentially providing vast improvements in computational power. While classical computers process information using binary bits, quantum computers rely on quantum bits, or qubits, which can take advantage of these quantum phenomena to perform computations more efficiently. Superposition is one of the key features of quantum mechanics that sets quantum computing apart from classical computing. In classical computing, a bit can only exist in one of two states at a time, either 0 or 1. However, a qubit, which is the basic unit of quantum information, can exist in a superposition of states. This means that a qubit can be in both the 0 and 1 states simultaneously, with each state having a certain probability of being observed when measured. The power of superposition lies in its ability to represent many possible combinations of states at once. As a result, quantum computers can perform calculations on multiple possibilities simultaneously, allowing them to solve problems more efficiently than classical computers, which would need to process each possibility one at a time. The principle of superposition is often illustrated with a simple example involving two qubits. While two classical bits can represent one of four possible combinations of states, 00, 01, 10, and 11, two qubits can exist in a superposition of all four states at once. This means that a quantum computer with two qubits can process all four possibilities simultaneously, drastically improving computational speed. As the number of qubits increases, the number of states that a quantum computer can represent simultaneously grows exponentially. This exponential growth of possible states is one of the reasons why quantum computing holds the potential to solve certain problems much faster than classical computers. While superposition allows quantum computers to perform parallel computations, entanglement is another crucial property that enhances their computational power. Entanglement is a quantum phenomenon in which the states of two or more qubits become correlated in such a way that the state of one qubit cannot be described independently of the state of the others. When qubits are entangled, the measurement of one qubit immediately affects the state of the other, regardless of the distance between them. This phenomenon allows quantum computers to perform operations on multiple qubits simultaneously, creating a network of interconnected qubits that can work together to solve complex problems. Entanglement is often referred to as spooky action at a distance because of the way it defies our classical understanding of how information can be transmitted. In classical systems, information is transmitted through physical signals, and the state of one bit can only influence the state of another bit if they are physically connected. In contrast, quantum entanglement allows qubits to influence each other instantaneously, no matter how far apart they are. This unique property enables quantum computers to perform tasks that would be infeasible for classical computers, such as factoring large numbers or simulating complex quantum systems. One of the key ways in which superposition and entanglement are used in quantum computation is through quantum gates. Quantum gates are the basic building blocks of quantum algorithms, similar to classical logic gates in traditional computers. However, unlike classical gates, which operate on bits that are either 0 or 1, quantum gates operate on qubits that can exist in superpositions of states. Quantum gates manipulate the states of qubits in ways that allow quantum computers to perform complex calculations. When qubits are entangled, quantum gates can take advantage of the correlations between qubits to perform operations that involve multiple qubits at once. Superposition and entanglement also play a critical role in quantum parallelism, which is the ability of a quantum computer to perform many calculations at the same time. This ability is a direct result of the superposition of qubits, which allows quantum computers to represent and process multiple possible states simultaneously. When qubits are entangled, their correlations enable quantum computers to perform operations on multiple states at once, further enhancing their computational power. Quantum parallelism allows quantum computers to solve problems more efficiently than classical computers by reducing the number of steps required to arrive at a solution. For example, in Shor's algorithm, a quantum algorithm for factoring large numbers, superposition and entanglement are used to perform multiple calculations in parallel. This quantum parallelism allows Shor's algorithm to factor large numbers exponentially faster than the best-known classical algorithms. The power of superposition and entanglement is also evident in Grover's algorithm, which provides a quadratic speedup for searching unsorted databases. By exploiting quantum parallelism, Grover's algorithm can search a database much faster than classical algorithms, making it a valuable tool for applications such as artificial intelligence and optimization. Despite the potential of superposition and entanglement in quantum computation, there are several challenges that must be overcome in order to build practical quantum computers. One of the biggest challenges is maintaining the delicate quantum state of qubits over time. Quantum systems are highly sensitive to their environment, and even small disturbances can cause qubits to lose their superposition or entanglement in a process known as decoherence. To overcome this challenge, researchers are developing techniques to isolate qubits from external noise and protect their quantum properties. This includes using superconducting circuits, trapped ions, and other advanced technologies to create and manipulate qubits with high precision. Another challenge in quantum computation is error correction. Because quantum computers rely on fragile quantum states, errors are more likely to occur during computations than in classical computers. Traditional error correction methods used in classical computing do not work for quantum systems, so researchers are developing new quantum error correction techniques to protect qubits from errors. One promising approach is the use of quantum error correction codes, which use multiple physical qubits to encode a single logical qubit, thereby reducing the impact of errors. However, quantum error correction requires a large number of qubits and introduces additional complexity, making it one of the major obstacles to building large-scale quantum computers. In addition to the technical challenges, quantum computation also raises important questions about the nature of computation and the limits of what can be computed. While quantum computers are expected to provide significant speedups for certain problems, they are not expected to replace classical computers for all tasks. Quantum computing is best suited for solving specific types of problems that are difficult or impossible for classical computers to solve, such as factoring large numbers, simulating quantum systems, and optimizing complex systems. For many everyday computing tasks, classical computers will continue to be more efficient and practical. Despite these challenges, the potential of superposition and entanglement in quantum computation is immense. As researchers continue to develop new techniques for controlling and manipulating qubits, quantum computers are expected to become increasingly powerful and capable of solving problems that were previously intractable for classical computers. In the future, quantum computers could revolutionize fields such as cryptography, material science, drug discovery, and artificial intelligence, providing new insights and solutions to some of the world's most pressing problems. Shor's algorithm is a quantum algorithm that revolutionized the field of quantum computing, particularly in the area of cryptography. It was introduced by mathematician Peter Shor in 1994 and provides a quantum solution to the problem of factoring large numbers, which is a task that classical computers struggle with. The significance of Shor's algorithm lies in its ability to factor large numbers exponentially faster than the best-known classical algorithms, making it a potential threat to the security of many cryptographic systems that rely on the difficulty of factoring large numbers. This capability has profound implications for the field of cryptography, which underpins much of our modern digital security infrastructure. The problem of factoring large numbers is fundamental to many encryption schemes, such as RSA, Reverse Shamir Adleman, which is widely used in securing online communications, digital signatures, and other sensitive information. In RSA encryption, the security of the system depends on the difficulty of factoring the product of two large prime numbers. Classical computers would require an impractical amount of time to factor large numbers, especially as the numbers grow in size. For instance, RSA encryption typically uses key sizes of 2048 bits or more, which are considered secure against attacks from classical computers. However, Shor's algorithm allows a quantum computer to factor such large numbers in polynomial time, which would break the security of RSA encryption and other cryptographic systems based on factoring. Shor's algorithm leverages the principles of quantum mechanics to achieve this exponential speedup. The algorithm uses quantum parallelism, which is the ability of quantum computers to explore many possible solutions simultaneously to find the prime factors of a large composite number. The basic idea behind Shor's algorithm is to reduce the problem of factoring large numbers to the problem of finding the period of a specific mathematical function. Once the period of the function is found, the factors of the large number can be determined with high probability. The key to Shor's algorithm's efficiency is the use of quantum Fourier transform, which allows it to find the period in much less time than any known classical algorithm. The impact of Shor's algorithm on cryptography is profound, as it threatens the security of widely used encryption systems that are based on the assumption that factoring large numbers is computationally difficult. If large-scale quantum computers capable of running Shor's algorithm become available, they could break the encryption of sensitive data, including government communications, financial transactions, and personal information. This has led to an urgent need for quantum-safe cryptography, which refers to cryptographic techniques that are resistant to attacks from quantum computers. In response to the potential threat posed by Shor's algorithm, researchers are actively working on developing quantum-safe cryptographic systems. One approach is to use encryption schemes that rely on mathematical problems that are believed to be difficult for both classical and quantum computers to solve. These include lattice-based cryptography, hash-based signatures, and multivariate polynomial encryption, among others. Lattice-based cryptography, for example, is based on the hardness of certain problems in lattice theory, which are believed to be resistant to attacks from quantum computers. Similarly, hash-based signatures rely on the security of hash functions, which are difficult to invert even with quantum computers. Another approach to quantum-safe cryptography is the development of post-quantum cryptography, which involves creating new cryptographic algorithms that are specifically designed to be secure against quantum attacks. These algorithms are based on problems that do not have efficient quantum solutions, making them resistant to attacks from both classical and quantum computers. The National Institute of Standards and Technology, NIST, is currently conducting a multi-phase project to standardize post-quantum cryptographic algorithms with the goal of providing secure encryption methods for the post-quantum era. In addition to Shor's algorithm, quantum computing has the potential to enable new forms of cryptography that are inherently secure against quantum attacks. One of the most promising areas of research in quantum cryptography is quantum key distribution QKD, which uses the principles of quantum mechanics to enable secure communication. QKD allows two parties to exchange cryptographic keys over an insecure channel in such a way that any eavesdropping attempt would be detected. This is achieved by encoding information in quantum states, which are fragile and can be disturbed by measurements. If an eavesdropper tries to intercept the quantum states, the information will be altered, and the parties involved can detect the intrusion. One of the most well-known protocols for quantum key distribution is the BB84 protocol, developed by Charles Bennett and Gilles Brassard in 1984. The BB84 protocol uses the polarization of photons to encode bits of information. The key idea behind QKD is that the act of measuring a quantum state disturbs it, making it impossible for an eavesdropper to obtain information without revealing their presence. This property, known as the no-cloning theorem, ensures that quantum key distribution is secure against eavesdropping. Even if an eavesdropper has access to the quantum channel, they cannot copy or measure the quantum information without altering the transmission, thereby making the eavesdropping detectable. Quantum key distribution is already being tested and implemented in real-world applications. For example, several companies have developed quantum key distribution networks that allow secure communication over long distances. China has launched a satellite, MIXIS, which uses quantum key distribution to establish secure communication channels between Earth and space. These developments demonstrate the potential for quantum cryptography to provide secure communication in the post-quantum era, where traditional encryption methods may no longer be safe. In addition to its potential in key distribution, quantum computing also has applications in other areas of cryptography, such as digital signatures and secure multi-party computation. Quantum digital signatures rely on the principles of quantum mechanics to create secure signatures that are resistant to forgery, even by quantum computers. Secure multi-party computation allows multiple parties to perform computations on private data without revealing their inputs, and quantum computing can enhance the security and efficiency of such protocols. Despite the potential for quantum computing to revolutionize cryptography, there are still significant challenges to overcome. One of the biggest hurdles is building large-scale, fault-tolerant quantum computers capable of running Shor's algorithm and other quantum algorithms. Current quantum computers are still in the early stages of development, with only a few dozen qubits available for computation. In order to run Shor's algorithm on large numbers, a quantum computer would need to have thousands, if not millions, of qubits, along with the ability to maintain quantum coherence and error correction over long periods of time. Researchers are working on improving quantum hardware, developing better error correction techniques, and exploring alternative quantum computing models to make large-scale quantum computing a reality. Quantum cosmology is a field that explores the intersection of quantum mechanics and cosmology, aiming to understand the fundamental nature of the universe its origins, and its large-scale structure. This interdisciplinary area of research combines the principles of quantum physics with the study of the cosmos, seeking to answer some of the most profound questions about the origin of the universe, the nature of space and time, and the role of quantum phenomena in shaping the cosmos. Quantum cosmology attempts to bridge the gap between quantum mechanics, which governs the behavior of particles at the smallest scales, and general relativity, which describes the behavior of gravity and the large-scale structure of the universe. At the heart of quantum cosmology is the quest to understand the very beginning of the universe. The standard model of cosmology, known as the Big Bang Theory, proposes that the universe began as a singularity, an infinitely dense point, around 13.8 billion years ago. According to this theory, the universe has been expanding ever since, giving rise to the vast, structured cosmos we observe today. However, the Big Bang Theory does not provide a complete explanation for the origin of the universe, particularly in the context of quantum mechanics. Quantum cosmology seeks to explore how quantum effects could have influenced the birth of the universe and the nature of the singularity itself. One of the key challenges in understanding the origins of the universe is the fact that general relativity and quantum mechanics are not easily reconciled. General relativity, which describes the gravitational forces that govern large-scale structures like galaxies and black holes, breaks down at extremely small scales, such as those found near the singularity of the Big Bang. On the other hand, quantum mechanics, which governs the behavior of particles at the subatomic scale, does not include a description of gravity. The lack of a unified theory of quantum gravity has been one of the biggest obstacles in understanding quantum cosmology. Physicists have been attempting to develop a theory that can combine both general relativity and quantum mechanics, known as a theory of quantum gravity, to explain the universe's origins more fully. One of the most well-known approaches to quantum cosmology is the idea of the quantum creation of the universe. This concept suggests that the universe may have originated from a quantum fluctuation in a primordial quantum field, such as the vacuum energy field. In this view, the universe did not emerge from an initial singularity, but instead from a quantum fluctuation that gave rise to the Big Bang. According to this idea, the laws of quantum mechanics allow for the spontaneous creation of the universe from nothing, a process that could be described using the principles of quantum field theory. This idea challenges the classical notion of the universe having a definitive starting point and suggests that the universe could have emerged from a quantum state that was not governed by classical physics. Another important aspect of quantum cosmology is the role of the wave function in describing the universe. In quantum mechanics, the wave function is a mathematical description of the probabilities of different outcomes for a system. The wave function allows for the superposition of various states, where a particle can exist in multiple states simultaneously, and only when measured does it collapse into a specific state. In quantum cosmology, the wave function is used to describe the possible states of the entire universe, including the different configurations of space, time, and matter. This approach allows for the possibility that the universe could have emerged from a quantum fluctuation, where the wave function of the universe describes the potential for different cosmic states to evolve over time. One of the most influential contributions to quantum cosmology came from the work of physicist Stephen Hawking. In the 1980s, Hawking and physicist James Hartle developed the no-boundary proposal, which suggests that the universe does not have a boundary or edge in the traditional sense. According to this idea, the universe is finite, but has no boundaries or singularities. In their model, the universe is described as a closed, self-contained entity that can be described using quantum mechanics. The no-boundary condition suggests that the universe did not have a traditional beginning, but instead emerged from a quantum state that had no distinct beginning or end. This concept is often described as a quantum creation of the universe, where the universe's wave function evolves from a state of no boundaries or time into the cosmos we observe today. The no-boundary proposal is closely related to the concept of imaginary time, a mathematical tool used in quantum cosmology to describe the universe's evolution. Imaginary time is a way of transforming the geometry of space-time into a form that allows for a smooth, finite beginning of the universe. In this formulation, time is treated as a complex number with a real part and an imaginary part. The use of imaginary time allows for the possibility of a universe that is finite in time, but does not have a singular beginning. This idea challenges the classical notion of a Big Bang singularity and suggests that the universe may have had a smooth quantum origin. Another important concept in quantum cosmology is the idea of the multiverse, which proposes that our universe is just one of many possible universes that could have emerged from a quantum fluctuation. According to this idea, the universe we observe may be just one of many universes that exist in a multiverse, each with its own set of physical laws and properties. The multiverse theory suggests that the Big Bang may have been just one of many such events, with each universe emerging from its own quantum fluctuation. This idea is supported by the notion of cosmic inflation, a theory that proposes that the universe underwent a rapid exponential expansion in its early moments, giving rise to a vast number of possible universes. Cosmic inflation is a key idea in quantum cosmology, and it suggests that the universe experienced a brief but intense period of expansion in the first moments after the Big Bang. During this period, quantum fluctuations in the fabric of space and time were stretched to enormous scales, creating the large-scale structure of the universe we see today. Inflationary models of the early universe propose that these fluctuations could have seeded the formation of galaxies, stars, and other cosmic structures. The theory of cosmic inflation is also closely tied to the idea of the multiverse, as it suggests that the inflationary process could give rise to many different universes, each with its own distinct characteristics. The study of quantum cosmology also has important implications for our understanding of space and time. In classical physics, space and time are viewed as continuous, smooth entities that can be described by the equations of general relativity. However, in quantum cosmology, space and time are viewed as discrete, quantized entities that emerge from the interactions of quantum fields. This view of space and time challenges our classical intuition and suggests that the universe may have a fundamentally different structure at the quantum level. Quantum cosmology also raises questions about the nature of time itself. In some models, time may not be a fundamental concept, but instead emerge from more fundamental quantum processes. This idea could lead to a new understanding of the flow of time and the nature of causality in the universe. Despite its theoretical promise, quantum cosmology faces many challenges. One of the biggest obstacles is the difficulty of testing the ideas and predictions of quantum cosmology through experiments or observations. Because quantum effects are most pronounced at the smallest scales, it is difficult to observe quantum phenomena on cosmological scales. Additionally, the early universe was in a highly energetic state, making it difficult to simulate or test the conditions that existed at the time of the Big Bang. However, researchers continue to explore ways of testing quantum cosmology. Through indirect observations, such as studying the cosmic microwave background radiation, the afterglow of the Big Bang, and the large-scale structure of the universe. Black holes are one of the most fascinating and mysterious phenomena in astrophysics. They are regions of space-time where the gravitational pull is so strong that nothing, not even light, can escape from them. This intense gravitational force is the result of a massive star collapsing under its own gravity, creating a singularity, an infinitely dense point at the center of the black hole. Around the singularity is the event horizon, the boundary beyond which nothing can escape the black hole's gravity. Once something crosses the event horizon, it is irrevocably pulled towards the singularity, where it is crushed to an infinitely small point. Despite their name, black holes are not empty voids, but rather contain enormous amounts of mass and energy in a very small space. The study of black holes began with the theory of general relativity, proposed by Albert Einstein in the early 20th century. According to general relativity, mass and energy can warp the fabric of space-time, creating what we perceive as gravity. The more mass an object has, the more it warps space-time, and in the case of black holes, the warping becomes so extreme that it creates a region from which nothing can escape. The first solution to Einstein's equations that predicted the existence of black holes was derived by the German physicist Karl Schwarzschild in 1916. Schwarzschild's solution described the geometry of space-time around a point mass, leading to the idea of a Schwarzschild radius, the radius of the event horizon of a black hole. While black holes were initially a theoretical concept, evidence for their existence began to accumulate in the second half of the 20th century. Astronomers observed that certain regions of space emitted intense gravitational radiation, and objects in these regions behaved in ways that suggested the presence of a massive, unseen object exerting a powerful gravitational force. One of the most compelling pieces of evidence came from the observation of stars orbiting invisible objects with enormous mass, such as the supermassive black hole at the center of our galaxy, Sagittarius A star. The study of these objects has led to the identification of black holes with a range of masses, from stellar mass black holes formed from the collapse of massive stars to supermassive black holes, which can have masses millions to billions of times that of the Sun. However, despite their well-established existence in the universe, black holes remained an enigma in terms of their behavior at the quantum level. In the 1970s, the British physicist Stephen Hawking proposed a groundbreaking theory that would connect black holes with quantum mechanics, a theory that would have profound implications for our understanding of both black holes and the nature of the universe itself. This theory, known as Hawking radiation suggests that black holes are not entirely black, but instead emit radiation due to quantum effects near the event horizon. Hawking radiation arises from the principles of quantum mechanics, specifically the concept of vacuum fluctuations. In quantum theory, even empty space is not truly empty, but is instead filled with virtual particles that spontaneously pop in and out of existence. These virtual particles are pairs of particles and antiparticles that momentarily appear and then annihilate each other, returning to the vacuum. However, near the event horizon of a black hole, these virtual particles can be affected by the intense gravitational field. When a pair of virtual particles forms close to the event horizon, the gravitational field can cause one of the particles to fall into the black hole, while the other escapes into space. The escaping particle is detected as radiation, which is now known as Hawking radiation. The key insight of Hawking's theory is that this radiation is not simply a result of the black hole's interaction with its surroundings, but rather a quantum mechanical process that occurs at the event horizon. In essence, the black hole is emitting particles and energy, which leads to the gradual loss of mass and energy from the black hole. Over time, this process can cause the black hole to lose mass and eventually evaporate entirely, a phenomenon that has been referred to as black hole evaporation. The emission of Hawking radiation has profound implications for our understanding of black holes. For one, it suggests that black holes are not completely black, but instead have a form of temperature. This temperature is inversely related to the mass of the black hole, meaning that smaller black holes have higher temperatures and emit more radiation, while larger black holes emit less radiation. This temperature is extremely low for large black holes, such as those that are millions or billions of times the mass of the Sun, but it becomes more significant for smaller black holes. As a result, smaller black holes are predicted to evaporate much more quickly than larger ones. Hawking radiation also raises important questions about the fate of information that falls into a black hole. According to the principles of quantum mechanics, information about a system state cannot be destroyed, but classical general relativity suggests that anything that falls into a black hole is lost forever. This led to what is known as the black hole information paradox. Hawking's theory of radiation suggested that the information inside a black hole might be lost when the black hole evaporates, challenging the notion that quantum information is preserved. The paradox sparked a heated debate in the scientific community and led to ongoing research into how the information that falls into a black hole might be preserved or retrieved. Several theories have been proposed to resolve the information paradox. One of the most popular is the idea of holography, which suggests that the information about the interior of a black hole is encoded on its event horizon, much like a hologram encodes a three-dimensional image on a two-dimensional surface. This theory, known as the holographic principle, suggests that all of the information that falls into a black hole may be preserved on its surface, even though it appears to be lost from the perspective of an outside observer. Another idea is that the information may be encoded in the Hawking radiation itself, although this is still a topic of debate. Despite the progress made in understanding black holes and Hawking radiation, there are still many unresolved questions. One of the biggest challenges is the need for a unified theory of quantum gravity. An understanding of how quantum mechanics and general relativity can coexist at the smallest scales, particularly near the singularity of a black hole. A theory of quantum gravity would allow scientists to understand the true nature of black holes, the role of Hawking radiation, and the fate of information inside a black hole. The study of black holes and Hawking radiation has far-reaching implications for our understanding of the universe. It challenges our classical concepts of space, time, and gravity, and it opens up new avenues of research in both theoretical physics and cosmology. For example, the discovery of Hawking radiation has implications for the study of the early universe. If black holes could have formed in the very early moments of the universe, they could have played a role in the cosmic evolution of the universe. Hawking radiation also suggests that black holes may be